All right, Mr. Dresser here. We're back for some more factoring. We're going to put it all together today and we're going to see if we can factor. First thing that I want to make sure we go over is the standard form of a quadratic. All of the problems that we've been factoring using the box have been quadratic expressions. For IM1, you might remember that quadratic is when your largest exponent is 2. So the standard form for quadratic is ax squared plus bx plus c. So your term with the squared on it, we consider that your a. And then the term with just the x on it, that's your b. And then your constant at the end is what we call our c. So for example, if I have the quadratic 3x squared plus 5x minus 7, then we would say the a value is 3, the b is 5, and the c is negative 7. And then we know it's a quadratic because of the x squared being the largest exponent. So it's important to note that as we're factoring, we're primarily factoring quadratic expressions, and we're going to use this to start solving quadratics in our next lesson. All right, so first thing we're going to do is we're going to look at some special cases of factoring. The nice thing about these is if you just factor using the box we've been doing, you can factor them the same way we've been doing it. So this first one, I'm going to make my box. And then as we've talked about quite a bit, first term goes in our first box. So our a goes in the first box. Our c goes in the last box. And then these two leftover boxes, we know we need to add to 8x. And then we need to multiply to the first box times the last box. So that's going to be multiplying to 16x squared. And then we go through and we find the numbers that multiply to 16, add to 8. That's going to be 4 and 4. So 4x and 4x. And then we take out our GCF from the top row. So that's going to be x. And then to get x squared, x times x. To get 4x, we need x times positive 4. And then to get 4x here, we need x times positive 4. So what you might notice on this one is our binomial on top is the same exact as our binomial on the side. So since we have a box where both sides are the same length, we call that a square, right? Just like the squares you've always done growing up, they have the same side lengths. So we call this a perfect square trinomial because when we factor it, we end up getting the same exact factors for the top and the side. So when we write our solution or our factors out, we don't have to write x plus 4 times x plus 4, although we could. But we could also simplify it and just put x plus 4 squared, because we know x plus 4 squared means x plus 4 times itself. So not really going to expect you to do too much with the vocabulary on this, but would want you to recognize that if we have the same binomial on the top as we have on the side, that we have a perfect square, and that's going to come, it's going to be something we do in a lesson next week where we complete the square. But we also know that if both factors are the same, we can rewrite it as x plus 4 squared, because it's the same thing twice. So here's another example. Go ahead and use our box. First term, first box. Last term, last box. Our unknowns must add to a negative 6x and multiply to x squared times 9, so 9x squared. We know we need to add to a negative, but multiply to a positive, which means I'm going to have two negative numbers. And after we guess and check for a little bit, we come up with negative 3x and negative 3x as our two leftovers. And then we're going to take out our common factor from the top row, and then work our way around the outside. X squared is x times x. To get negative 3x, we need minus 3. And to get negative 3x, we need another minus 3. So again, this is another special case. It's a perfect square trinomial. Perfect square because this side of the square is x minus 3, and this side of the square is also x minus 3. So when I write my final set of factors, I don't have to write it out twice. I can just write x minus 3 squared. And we know that that means x minus 3 times x minus 3. Two more examples. Just for good practice. First term, first box. last term, last box, we need to add the 6x and then multiply. Make sure you multiply both of those boxes together to get 9x squared. This time we're going to have positive 3 for both unknowns, so 3x, 3x. Take out our GCF from the top row. You can't put 9 in 1 because you need to take out common factors. So sometimes people will just start whatever multiplies to 9, they'll just put 9x and x and think that they're fine. But you have to be careful. You always have to take out whatever the GCF is. So our GCF of this row is 3x, which means this one has to be 3x. This one has to be positive 1. And then to get 3x, we need 3x times another positive 1. And again, it's another perfect square trinomial because both binomials are the same. So we could write that one as 3x plus 1 squared. All right, one more example. First term, first box. Last term, last box. We must add to negative 4x and then multiply to a positive 4x squared. Multiply to a positive but add to a negative, it's going to be 2 negatives. And you probably already got it. It's going to be negative 2x and negative 2x. Factor out our GCF from the top. I'm not going to take out x. Well, I am going to take out an x. So I'm not going to take out just x because I can also take out a 2 from the 4 and the 2. So I'm going to put 2x out there. To get 4x squared, this also has to be 2x. 2x times negative 1, and once again we have another perfect square. So again, it is a special case. There are shortcuts where you can look at the problem and see that there's a pattern and you can come up with a kind of a cheating way to do it. But to be honest, it's pretty hard to learn and memorize. So it's easier to just use the box. And as long as you can use the box, it doesn't matter if it's a perfect square trinomial or not. We know how to factor it. The next special case, this one's called a difference of two squares. And what you might notice when we go to factor this, we only have 2 terms. All the other box problems we've done so far have had 3 terms. We've had the A, the B, and the C. But this one is missing something. If we go back to the idea of standard form, ax squared plus bx plus c, which of those does this problem not have? That's right, there's no middle term. There's no b to the x, or bx. So I could rewrite this problem as 4x squared plus, and then since there's no b's, I can put 0x. So I'm going to rewrite it 4x squared plus 0x, and then my c value, that minus 9, would still go at the end. So by rewriting it with a 0x, we now know that if we use the box, we're still going to put our first term in the first box, last term in the last box, but now what they need to add to is 0x. So I'm going to put my 0x down here. And to multiply, I still need to multiply to this diagonal, which is negative 36x squared. So I know that my 2 numbers have to add to 0, which means they're going to be opposite numbers. So for example, negative 5 and positive 5, they add to 0. They'd be opposites. So I need to find which opposites also multiply to negative 36x squared. And after a while, well, probably pretty quick, because you really just take the square root of 36. You end up getting 6x and negative 6x. And so then I go ahead and take out my greatest common factor, which will be 2x. To get 4x squared, I also have 2x. To get 6x, I need plus 3. But unlike a perfect square trinomial, it's not going to be 2x plus 3 and 2x plus 3. It's going to actually be 2x, and then to get the negative, I need minus 3. So I can't write this out as 1 parentheses squared, because these are not the same binomials. You've got plus 3 in one, and you've got minus 3 in the other. So when I write my final factors down, I do need to put both the 2x plus 3 and the 2x minus 3. So again, it's just the same as any other factoring using the box problem. The only thing we had to do is recognize we didn't have a b value. So we put in 0 for our b, and then we go ahead and solve it, or factor it just like the other problems. All right, so another example. We have our A, we have our C, right? There's no variable attached, so that's our constant or our C, but we don't have a B. So I can rewrite this as x squared plus 0x minus 49. I can then fill in my box. First term, first box. Last term, last box. What do they need to add to? That's right, they don't have to add to anything. 0x. And then multiplication wise, they do need to multiply to negative 49x squared, which in order to multiply to 49 and add to 0, we take the square root of 49, which is 7. So we end up getting a positive 7x and a negative 7x. That will add to 0, but still multiply to the negative 49x squared. And then finally, take out our common factor, which for the top row is just the x. To get x squared, we need another x. To get positive 7x, we need plus 7. And to get negative 7x, we need minus 7. So x plus 7 times x minus 7. So again, difference of two squares, you can factor using the box, just put a 0 in the middle. I do like to show kind of the shortcut for the difference of two squares, because it is one that I think is pretty easy to recognize, and if you understand it, it's a shortcut you can use. However, if you get confused by the shortcut, don't worry about it. Just continue to use the box and plug in 0 for your B. But to explain difference of two squares, the first thing we have to make sure we know is what the word difference means. All right, so when we're talking about mathematics, when we're talking about difference, difference means we are going to subtract. So the only way you can have a difference of two squares is if you have a subtraction sign. So the problem has to be a subtraction problem. The second thing is it's a difference of two squares. So what are perfect squares? Well, a perfect square is something like 36, because to get 36, I can do 6 times 6. So both sides are the same length, 6 and 6, and they make the area 36. Or if we had 25, we could do 5 and 5. Those are the same length, it's a square, and they make 25. So you're probably familiar with most of these, right? 1, square root of 1 is 1. 4, square root of 4 is 2. 9, square root of 9 is 3. 16, 4. 25, right? It's 5. If we go up here, square root of 121 is 11, right? So it's a perfect square because we can take the square root of it and get a whole number. Similarly, you can have perfect squares with variables. If you have x squared, that's just simply x and x, so it's still the same side length. If you have x to the 4th, and these are definitely not drawn to scale, but hopefully you get the point, you could have x squared and x squared, so that would also be a perfect square, because you can take the square root and you get x squared. So again, don't want to totally overwhelm you with this, but if you find it interesting, it can be helpful. For example, the square root of 4x to the 32nd, the square root of 4 is 2. And then for the exponent, since you add to get exponents, if you just cut it in half, both of them would be to the 16th power. So if you did 2x to the 16th times 2x to the 16th, you'd get 4x to the 32nd. That's why this is considered a perfect square. But anyway, most of the ones you'll see are just going to be kind of the more common ones numerically, and then you'll see x squared a lot, which we know is just x times x. So we know difference means subtract. We know what perfect squares look like. So what does a difference of two squares look like? It just means you have literally a difference of two terms that are both perfect squares. So the way we can do this as a shortcut is if we take the square root of x squared, it's going to be x. If we take the square root of 9, it is going to be 3. And in order to multiply to get a negative 9, we know the only way to multiply to get a negative, so I'm going to circle my negative here. The only way to get a negative is if you multiply a positive times a negative. So if we were to factor this using the box, we would end up getting x plus 3 times x minus 3. If you don't believe me, try the box. It works, I promise. Here's another example. I recognize it's a difference because of subtraction. I know this is a perfect square because the square root of, let me get this started here. The square root of 4x squared is 2x, because 2x times 2x is 4x squared. And then I know that 49 is a perfect square because if I take the square root of 49, I get 7. And then because it's a difference, we know that we end up getting a negative number, which means we have to multiply a positive 7 times a negative 7 in order to get that negative 49. So again, if you have a difference of two perfect squares, we can automatically break it up into those two parentheses, and then you take the square root of the first term, and that goes in the first spot of each parentheses, and then the square root of your c value, and that goes in the back spot of each parentheses, and then to get a negative, you need one positive, one negative. So one more example. Square root of 25x squared is 5x. Square root of 81 is 9. And then in order to get that difference, right, it has to be subtraction. If it's addition right there, it doesn't work. It has to be subtraction. You get one positive and one negative. So difference of two squares, nice little shortcut. So if we look at these examples, we can determine pretty quickly to see if they are a difference of two squares or not. This one I know x squared, the square root would be x. 100, the square root would be 10. And then it is a difference because of the subtraction. So square root of x squared, I get x and x. Square root of 100, I get 10 and 10. And then to multiply to negative 100, I need a positive 10 and a negative 10. Just so you know that this really does work, let me give you an example of how we would do that one with the box. Right, we have x squared minus 100. So we recognize it's missing the b value. Right, so I can write x squared plus 0x minus 100. First term, first box. Last term, last box. I need to add to the middle. So we need to add to 0x. And then we need to multiply to this diagonal, which is negative 100x squared. And in order to multiply to negative 100 and add to 0x, we need to have 10x and negative 10x. And finally, we can take our common factor out of the top, multiply around the outside to get x times x. To get 10x, we need x times positive 10. And to get negative 10x, we need x times negative 10. And what do you know? X plus 10, whoop, x minus 10. Got it. So if you want to use the box, use the box. If you forget the difference of two squares, that's totally fine. Just put the 0 in the middle and use the box. But if you can memorize the whole distance of two squares, difference of two squares idea, then it does give you a little bit of a shortcut. So again, just kind of going through these quickly. Is this a difference? No, that's the sum, that's addition. So nope. Not a difference of two squares. We can't use the shortcut. Has to be subtraction. Is this a difference of two squares? Well, I've got difference. Square root of 36x squared is 6x. And the square root of 1 is 1. And to get the negative, I do a 1 positive, 1 negative. So voila. Save ourselves some time. If you recognize the difference of two squares, you can do the shortcut. This last one, it's got a difference. That's good. Square root of 49x squared is 7x. But what's the square root of 2? That is not a perfect square. Not a perfect square. Therefore, nope. We are not going to use the shortcut for that problem because it is not a difference of two perfect squares. All right, if we were in class, I'd have you write your own example right now. So I'm going to go ahead and call on somebody. Let's go with Casper. Casper. You know, I couldn't hear him. That's funny. Anyway, I think he might have said x squared minus 64. Would that work? Is that a difference of two squares? Well, square root of x squared is x. Square root of 64 is 8. And to get a negative, we need plus, minus. All right, let's take someone else's example. Who else do we got here? Yep, still nobody here. This is kind of sad. I miss you guys. I really do. Here's another example. Let's get crazy here. 144x squared minus 81. No, I don't want to do that. I'm going to go 49. We got a difference. That's good. Perfect square. What's the square root of 144x squared? Well, the square root of 144 is 12, and the square root of x squared is x, so we get 12x. And then the square root of 49 is going to be 7. And then to get a difference, that's positive times negative. So again, if you don't want to do it this way, you don't have to. You can use the box. Just plug in a 0 for your middle term, and you're good to go. All right. Whew. You might want to take a break. If you need a break, that's fine. That's kind of a lot of information. I get it. It's a lot coming at you in one day. We're about to get into the big daddy of them all, which means we are going to put it all together. So when I think about sports, I think about basketball. I coach basketball. I like basketball a lot. What's up, Major? Glenn? I better stop naming people or I'm going to forget people, so I'll stop there. But anyway, in basketball, you've got offense, you've got defense. Sometimes in practice, we work on the offensive stuff for a little bit, then we work on the defense for a little bit, but then we put it all together and we actually play the game of basketball. Kind of the same thing's been going on. Last week, we talked about the GCF, right? The greatest common factor. So for example, if we have 4x plus 12, our greatest common factor was 4, right? And then we had x plus 3 is our remaining factor. And we could always double check that by multiplying it out. Or you might have used the box to do this, right? We had 4x plus 12 is what we started with. And then we reverse distributed. And so once we pulled out that 4, we knew to get 4x, we needed x. And then to get 12, we needed 4 times 3, right? So that's where my x plus 3 came from. But that's called factoring out the GCF. And then we've been factoring our quadratics using the box. I'm not going to put another example up because we've done like 1,000 of them. But we'll call this our offense for right now. We'll call this our defense. So we've been kind of teaching you how to play offense. We've been teaching you how to play defense. Now we're going to combine them and we're going to play the factoring game. So we are going to start factoring completely. To factor completely means we're going to do both things. We're going to look for a GCF. And then we're going to look to see if we can factor the quadratic using the box. Not every problem will have a GCF, and not every problem can be factored using the box, but we're going to try. So, for example, this first one, if I look at all 3 terms, I might recognize that 9 goes into all 3 of those. So we do have a GCF. I'm going to, real quick, make a little note over here on the side. We're going to 1, look for the GCF, and then 2, use the box. And then I will show you later how if you forget to take the GCF out at the start, we can still find it later. But the problems are going to be much simpler if you take the GCF out first, if it does in fact have a GCF. So this first one I can take out a 9. And if I take out a 9, I know that to get back to my 36x squared, I need to do 9 times 4x squared. To get back to negative 36x, I need 9 times negative 4x. And then to get to 9, I just need 9 times 1. So however many terms you start with, since I had 3 terms, you will always have 3 terms inside your parentheses after you take out your GCF. So make sure you don't forget about this 3rd term here. So once we've done that, we now need to factor our quadratic that's inside the parentheses. So here's where we're going to make our box. First term, first box. Last term, last box. We need to add to the middle. So add to a negative 4x. and then we need to multiply to a positive 4x squared. So we sit here, we brainstorm a little bit, and eventually we get to negative 2x and negative 2x, which means our top row has a common factor of 2x, which gives us 2x, and then to get that we need minus 1, and to get this one we also need minus 1, so we could write that as 2x minus 1 squared. That's one of our perfect squares. But this is not our final factored answer, because what else did we do at the start? We took out the GCF. So this GCF, this greatest common factor, is in fact one of our factors. It's one of the things that we're multiplying together. So we need to drop it on down and make sure we put that 9 out front, because it was one of our factors. So in the end, by factoring completely, we have a 9, and then we have 2x minus 1 times 2x minus 1. This is some good stuff, man. You guys are getting into, I call it big kid math. I don't want to offend you, but anyway, we're growing up. We're getting there. This is some legit math right here. This next one, I noticed two things. First, 2 can go into each of these. And then also, we never want our a to be a negative. So I'm not only going to factor out a 2, I'm also going to factor out a negative. So my GCF on this problem is negative 2. Going back to this one, my GCF was positive 9, right? We made sure we put that GCF in the final answer. So same thing here. I know that my GCF of negative 2 is going to be a part of my final answer. When I go back to figure out what goes in here, to what goes in my quadratic expression, I'm going to divide each of these by the common factor of negative 2, and I get x squared minus 2x minus 48. Again, the way I can make sure that's correct is if I multiply negative 2 times x squared, I get negative 2x squared. Negative 2 times negative 2x gives me 4x, and negative 2 times negative 48 gives me positive 96. So you can always check as you go. So we know that this is going to be one of our factors, but now we're going to go ahead and figure out, do we have more factors that we can use the box for? So I'm going to put first term, first box, last term, last box. We need to add to negative 2x, and we need to multiply to negative 48x squared. So again, some strategy on here. I know it needs to multiply to a negative, so I have one positive and one negative. But I also know that the absolute value of the two numbers is close together. They're only 2 apart. So I need to find two numbers whose absolute value are only 2 away from each other, but still multiply to 48. And so I end up getting 6x and negative 8x. And again, I know that 8 is the negative because when I add them, I need to get a negative. So I need more negatives than positives. Go ahead and factor out that top row. Get x squared, we need x up there. To get 6x, we need plus 6. And to get negative 8x, we need minus 8. So in the end, our factors were x plus 6, x minus 8, and oh yeah, don't forget, we took out the GCF of negative 2. We need to bring that on down. And there is our completely factored expression. Now some of you are probably thinking, well, what if I forget to bring that negative 2 down? Am I still right? No, you're wrong. You didn't do it all the way. You get partial credit though, because you did a good job. But if you take out a GCF, you got to bring that GCF down. It is part of your factors. All right, 2 more examples here. Look for the GCF first. GCF of this is 3. Leaves me with x squared minus 4. When I look at the x squared minus 4, it might pop into my head, hey, that's a difference of 2 perfect squares. And if that does, then great, you can automatically put your answer down. If you didn't recognize that, then you might rewrite this as x squared plus 0x minus 4. Plug that in the box. X squared,